All right, hi, my name is Vivekanand and I'm a part of the Ashton Graybill Spatial Orientation Lab, and today I'll be talking about gravitational cues and balancing. Now, I took this picture at the tippy top of a sacred mountain, and the question that it inspires is, how are we able to balance? A simple question which still does not have a good answer. And one reason why is because balance control depends on a variety of different sensory information, from the visual to the vestibular, from the somatosensory to the proprioceptive. And today's presentation will focus on the role of the vestibular system on balance control. Now, what we know is that the vestibular system is a crucial component of balancing, and that is exemplified by this video over here, where a woman with vestibular loss is blindfolded and asked to balance. And you can see that she has great difficulty. And so while we know that balance control is difficult, or rather crucial, what we don't know is what components of the vestibular signal are important, how those components of the vestibular signal are integrated together to eventually create motor commands. So to be able to explore that, today I will talk about two different conditions. And first I'll describe these conditions, and then I'll explain to you how the vestibular system works and how the vestibular system and the vestibular signals are different in each of these conditions. So in the first condition, I take the humans and I strap them into this beast known as the Hulk. And the Hulk is programmed to behave like an inverted pendulum. And an inverted pendulum is just like balancing a pencil on your fingertip. It turns out that the inverted pendulum is a good first approximation for human balancing. And just like a pencil that you're trying to balance, if you do nothing, which is what I'm doing here, you will fall down either to the left or to the right. And there are safety mechanisms programmed at positive and negative 60 degrees, so that if you hit that point, you will be reset to the 0-degree point, and the trial will begin. Now, subjects are given the task: balance this machine to the best of your ability right at 0 degrees, and use a joystick to be able to accomplish that. They are blindfolded, and they wear noise-canceling headphones. And as a result, they rely primarily on their vestibular system and, to a secondary extent, their somatosensory system, because they're getting tactile cues through their skin as they press against that machine. What I should also say is that this paradigm is unique. And it's unique because you cannot use the biomechanical properties of your legs. And you cannot use the reflexes that you typically use to balance. And so as a result, you can sort of analyze what learning goes on in the absence of reflexes. And that was the topic of my first pizza talk. So if you are curious about that, ask me at the end. In the second condition, I take the people and I tilt them backwards by 90 degrees, and they perform the same exact balancing task: balance at 0 degrees. Now, for those of you that have not seen this presentation before, I would encourage you to come up with an answer to the following question. Do you think it would be easier to balance on your back, or do you think it would be harder? Do you think that this difference would be very significant, or do you think it would be nuanced? In many ways, being on your back is not that non-intuitive. Many of us sleep on our backs. Some of us do intense activities that require balancing on our back, such as jiu-jitsu. So, what is your guess? Make a guess, and then you'll be excited for my results. So to understand how the vestibular signal is different in each of these cases, we're going to take a magical school bus journey into the inner ear, which is where the vestibular system resides. And the vestibular system is composed of two components. The first are the semicircular canals, which are filled with fluids, and what they detect is angular acceleration. So movements like this, movements like this, and movements like this, these are all activating my semicircular canals. And as far as we can tell from the literature, the information from the semicircular canals are the same in the upright as they are on your back. So far there's no difference. But the story becomes juicy as we go into the second component of the vestibular system, which are the otoliths. And the otoliths are these fine hairs that are suspended in gelatinous material, adorned by gorgeous crystals, and what they detect is linear acceleration. So if you're in a car and you begin to accelerate, those little hairs will bend backwards, telling you that you're experiencing linear acceleration. But they also detect linear acceleration due to gravity. So for example, if you're wearing your predator-prey pants that you designed all by yourself and you're tilted by 10 degrees, the little hairs will tilt that much, informing you that you're 10 degrees from the gravitational vertical. If you're tilted even more, let's say by 45 degrees, those hairs will tilt even more, telling you that now you're 45 degrees from the gravitational vertical. So in the upright condition, you can use information from your otoliths to determine your angular position. And here's where things become interesting. Because when you're on your back, then those little hairs will be tilted backwards, telling you that you're 90 degrees from the gravitational vertical. But they'll say that same exact thing whether you're here or you're here. You don't get any additional information about your angular position. So to summarize, when you're on the upright or on the back, your semicircular canals will give very similar information. In contrast, if you're in the upright, you can use your otoliths, you can use gravitational cues to figure out your angular position, but you cannot do that when you're on your back. And so the question of my presentation becomes, how important are these gravitational cues? Do you really need them? And if you look at prior literature, what they've done in these prior experiments is they've taken the humans, they've put them in these robotic chairs, and they've done yaw rotation, which is different than the rotation my subjects experience. They experience rotations like this. In prior literature, they rotate people like this. When you rotate someone like this, you're only activating canals because your head is not tilting. And what people have found in these experiments, when you rotate them and then you ask them, how far do you think you've gone? These people who are blindfolded are very accurately able to say how far they were displaced. And what these literatures or these papers conclude is that must mean that the canal's angular acceleration information is able to be properly integrated into angular position. And therefore, what these papers would predict is that there really shouldn't be a big difference between upright and the back. Sure, the back may be a little bit worse because you don't have gravitational cues, but you should still be able to do the task because you can integrate your information from angular acceleration. So to experiment with that, I have two groups. The control group does upright balancing on day 1, and the experimental group does balancing on the back on day 1. And both groups get 20 trials with 100 seconds cumulative of balancing per trial, and all trials are the same. Balance to the best of your ability at 0 degrees. After every 4 trials, they get a minute break. In terms of organization, 4 trials equals to 1 block. So here we are at the foothills of my results. I hope at least some of you are excited to see what happens. Even for those of you that have seen my presentation before, previously it was N of 6, now I've got 20. So that's kind of exciting. On the x-axis, I have block number. On the y-axis, I have standard deviation of angular position. So that's just measuring how much variability there is. What I've shown you over here is people who do upright balancing. And what you can see is that people in upright balancing learn to do the task. They learn to minimize their variability that is supported by this ANOVA over here that I provided. And also these stars are t-tests done between the first block and the second, the first block and the third, and so on. So you can see that they reduce their variability. And now here comes the back condition. And what we see is it's a little crazy, because not only is the back condition very difficult, people are not collectively learning to minimize their variability. And that's pretty crazy, because they're in this machine for 40 whole minutes. And so again, it's statistically different to these two groups. Now in my last pizza talk, someone asked the question, well, okay, you've shown that gravitational cues are important, and you've shown that angular acceleration is not being properly integrated initially. But what happens if you would expose these people to the same condition again on a second day? Would somehow that awaken their ability to integrate the information and therefore do the task well? So I put some of these humans back again in day 2 in that machine, and there they were for 40 minutes. So what do you think is going to happen? Will these humans learn, or will they be stuck in a purgatory of just crashing and not being able to control the machine? And what we find is that they are poor, unfortunate souls, because collectively as a group, they're still not learning on day 2. There's no statistical difference between block 1 and block 5. What's more is that if I compare their performance on day 1, first block, to their performance on the last block on the last day, there's still no statistical significance in their ability to minimize variability. And they're still statistically different than the upright group. To understand and get a little bit more intuition into what is going on, let's take a journey into the raw data itself. And so on the x-axis here we have time, and on the y-axis we have angular position, which is represented by that black line, and the red line is the joystick. And this person is doing upright balancing. She's been in the machine for 40 minutes, and you can see that she's mastered the task. She's oscillating a little bit to the left and right of 0 degrees, doing a pretty A+ job. Now let's take a look at someone who's been placed in the machine for 40 minutes on the back. What do you think is going to happen? You know that the standard deviation is going to be greater, so you may expect that they'll be just all over the place as opposed to really focused. So let's take a look. And what we find is something unusual, because there's a pattern here. It's not just random flailing around. What you see over here is that they begin to drift, and they begin to almost oscillate at 20 degrees as if that were 0 degrees, and then they again begin to drift and drift and drift until they crash right at 60 degrees. Now, this is seen in varying amounts in all participants, and majority of the time, people are generally surprised that they're so far away from 0 degrees, even on the second day of exposure. So now, some of the skeptics in the audience will say, well, you've only shown me 2 graphs, one of which shows drifting. How can you prove that this occurs across pretty much everyone and across pretty much all trials? And the answer is the stabilogram diffusion analysis. In years prior, I've spent a good amount of time sort of showing you where this diffusion function comes from, but in this year I don't have time, so I'm just going to tell you how to interpret my graphs. The basic idea is that I can take this complex trial raw data with time and angular position, and by using the SDF, the stabilogram diffusion function, I can turn it into an elegant 2-piece graph, which has time interval on the x-axis and mean squared angle, just like a measure of distance really, on the y-axis. And what these 2 parts mean are the following. In the short time interval, people let the machine drift. That's what the diagonal line means. The mean squared angle increases. So the machine drifts and drifts and drifts, and in the long term, what they do is they start making motions to pull themselves back. So again, I went through it quickly. All I want you to take away is that there are 2 pieces, a drifting piece and then a consistent pullback piece. If you look at actual human balancing, what we see is that those 2 pieces are there. Human balancing is about drifting and then pulling yourself back. If we look at my data from upright, this is segregated by block number. There's a whole bunch of metrics I can pull out from this, which I won't do right now. But again, all I want you to concentrate on is the fact that there are 2 of these stages here, and you clearly see that they have a drifting stage and then they have a correction phase. And now here comes the back. And what you see is that that it's no longer this 2-stage, but rather it is prolonged. That this drifting stage goes on and on and on, and they drift and drift and drift. And what's more is on the second day, this same sort of behavior, this trend, is still there. Now, before I go on to the next section, I have a whole bunch of other mathematical metrics that actually can describe what the difference, quantify the difference between upright and back, which I don't have time to go into. But if you're curious, you should totally ask me and take a look at these 2 little cuties that I brought in. Here is upright balancing, and here's balancing on your back. If you're intrigued, you can ask me at the end what they exactly are. Right. So far what I've shown is that on the back, subjects have great difficulty balancing. This is because they cannot use their gravitational cues from the otolith to determine their position. And what this suggests is that your semicircular canals are not able to properly integrate the angular acceleration information to get angular position. What it also suggests is that gravitational cues may serve as a way to calibrate the canal signal when people have access to them in the upright condition. But there still is a lingering question of the many questions, which is that if you don't have a proper position signal, why wouldn't you just randomly go all over the place? Why is there this drifting? That's a pattern. So to understand why that's happening, to explore that, what I have is I did a small computational model. Now, this computational model is in its infancy. It is just a few weeks old. It can barely walk or stand. So just keep that in mind. It's a first pass, and there's a lot of improvements I have to do to it. But it's cool enough where I thought I'd show it to you. So I used a virtual simulation, which was made by the brilliance of Sasha and Heather from my lab. And this virtual simulation has all of the same properties as the main Hulk. It's the same exact program that controls the machine. And I made a controller, basically a computer program that was given the task to actually balance the machine. And what I told this computer program was, I said, make a joystick movement every 500 to 1,000 milliseconds, which is what the humans do. And I said, I gave this computer controller sensory information about position and velocity. And basically, it averaged the two of these and then scaled the joystick, movements in relation to this. And what I found was the following. Here's human balancing. You've already seen this plot. And on the bottom is the computer balancing the machine. And you can see that they're very similar. And if I use my mathematical metrics, they come out to be very similar performance. Now, for the back condition, the idea is that there's improper integration. People don't have a good sense of their position. Therefore, they rely primarily on their velocity. So as a first step, as just a very simplified first step, I said, I'm just going to give this controller velocity information. And the computer will make joystick deflections that scale with the magnitude of the velocity. Just that simplification, sort of ignoring the improper integration. And here's human balancing that you've already seen, and you can see that there's drifting going on. This is a graph that you've already seen before, and now here is what happens with the computer. And what you see is that there's drifting until they crash, then the computer resets, and then again they begin to drift. So you can see that some of this drifting is replicated by this computer when it's only given a velocity signal. And I'm running out of time, but the SDFs are the very similar looking between humans and the computer. The black line is upright, the red line is the back condition. But what these results suggest is that drifting in part is caused by a poor position signal and by velocity control. The idea being that the machine initially drifts, the person makes a joystick movement that brings them somewhere midway, the velocity equals 0, they have no idea where they really are, and then because the velocity equals 0, they think they're at maybe 0 degrees, and they in that fashion drift away until they crash. In the future, to understand this improper integration better, I will passively rotate people, so they'll be on their back, they'll be blindfolded, they won't have control over the machine. I'll just move them and then ask them how far have they gone, and then make a model based on what kind of improper integration that's occurring. The last sort of thing that I want to talk about is that subjects do show learning in other metrics. So pound for pound, almost everyone shows learning for crashes, minimizing their crashes. In addition, there are some subjects, if I group them by good performers, that actually show learning in the standard deviation, in decrease in the standard deviation. And they use cognitive strategies to do that. So if you're curious about it, ask me at the end what I mean by that. Nevertheless, 90% of all subjects, even on day 2, even those that learn to minimize their variability, say they have no idea where they are. They can control and decrease the variability a little bit by using cognitive strategies, but still they don't know where they are in space, which is pretty interesting. All right. I would like to thank the lab, which is a beautiful and wonderful lab. In particular, both Jim and Paul are absolutely amazing and beautiful individuals who have allowed me to grow and bloom. Paul has even taught me how to raise bees in my backyard, which has been a great summer adventure. I'd like to also thank Sasha and Heather, who have done immense amount of programming with the Hulk and have taught me how to tame that beast. I'd like to thank my committee, who is composed of a really wonderful group of people. And finally, just really quickly, I would like to have you concentrate on the names of these mentors. So I do a small high school program where in the summertime, really passionate young high school students from Malta High come over, but these kids have no opportunities, and these mentors who I have nothing to give to devote their time and let these kids really experience a life-changing event. I'd like to thank also the faculty that are associated with these labs. This year we also had a biochemistry and 3D printing course for the kids, which is really pretty amazing. So I'd like to thank all the people that are involved with that. And also this year we had Francesco, who created and taught a Python programming course, which is really cool too. All right, questions? So you're asking about the threshold of activation. Yeah, so there are differences in your threshold of activation for upright and the back, but for the large amount of velocity and acceleration that these guys feel, it's pretty much the same, in terms of activation thresholds. Yeah. Oh.
There's a second part to this. Mm-hmm. Would you speculate that in G0 they would react the same? So in G0 this and this would be basically the same.
Yeah. Yeah, no, it's a really cool question. So, I would guess that in G0, even upright balancing, if you don't have visual information, would be very similar to back balancing. Because once you don't have those gravitational cues, it becomes very difficult to know where exactly you are, especially as you start moving around. Yep.
So the model does even worse than the people do.
Yeah.
Which suggests to me that you do have some integration just over a shorter time window than you need. Which suggests that if you were perturbing them over that short time window, they'd be able to deal with that. In other words, you could potentially measure the integration time over which they can hold on to.
That's a really cool idea. Yeah, so so in my model, I didn't put any improper integration, but if I did, then most likely there'd be more drifting. And one approach is that way, which we may do, or the other approach is just to do the passive rotations, which is kind of similar, and from there determine what the integration looks like, and then put in the model. Yep, Scott.
Curious about the cognitive strategy. Do you provide feedback between day 1 and 2 as to what their performance was?
No, I don't. So basically, the cognitive strategy is, so they don't know where they are, they need an extra cue. And the extra cue comes in the form of what they're doing with the joystick. The basic idea is that if you're at 0 degrees, you can pretty much let go of the joystick and the machine will be balanced, and then internal noise will cause it to start to slowly move to one side or the other. So what happens in this machine is most people will misidentify velocity equals to 0 as being the 0 degree point. And the people that realize, oh, even though my velocity is 0, my joystick is actually deflected, that must mean I'm not at 0 degrees. So these people will keep tapping the joystick until they can almost let go of the joystick. And when they can let go of the joystick, they know they're at 0 degrees. So that's the cognitive strategy that they're using to be able to do the task. And every single one that minimizes their variability says that in either an intuitive way or a very quantitative way. Yeah.
Are you able to play with the rate of acceleration when they're on the back?
Yeah, so it's really cool. All of mine have been adjusted so that it's like wicked tough in the upright condition so I can see learning. But Heather and Sasha work with a lower G value, like a lower rate of acceleration. And they're also doing stuff on the back. So, eventually we're going to compare our two and see how they're different.
Is there any way that have you looked at different acceleration rates on the back to see if maybe there's like some threshold at which they can sense a certain acceleration or not?
Yeah, so in terms of the threshold, other people in other literature have already found the actual thresholds of when the otoliths or the canals will activate. In terms of our experiment, we've started, so Heather and Sasha are working on lower G values, lower acceleration values to look at it. I haven't myself adjusted it yet to see what happens. But it's definitely a cool concept. Yeah.
So what happens if people are laying on their back and you prop your head up with the pillow? Does that improve performance or
So one of the undergrads with Sasha, what they're doing is they're actually pitching the people back and trying to see at what angle do things start going bad. Potentially, right. If you can raise the head a bit at a pitch angle higher than 90 degrees, you'll have otolith information. You should be able to perform a bit better. So, that's a really cool idea. All right, all set.